Okay, so this is the third part of the review of L'Hopital's rule, in which we cover the indeterminate powers, and those are the limits of this form: 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity. So we will do 3 examples like this. The first example, limit as x goes to 0 from the right. A simple example, sine of x to the power of x. So what did I say back in when we did this in class? The idea is to express this exponent as a product, right? So if you use direct substitution, the base here, sine of 0 is 0, and the exponent obviously goes to 0. So what can we do? We can express, so just recall that a is equal to e to the power of ln of a. So I'm going to use this property to rewrite this limit as e to the power of ln of sine of x to the power of x. And now, as you can see, dx appears here only in the exponent, so from Cal 1 we know that this can be written as the limit of a limit of ln, of sine of x to the power of x. And then if we can evaluate this limit, then this is just going to, if this limit converges to some constant, this is going to be e to that constant, and we are done. We'll evaluate this limit on the side. So limit as x approaches to 0 from the right, ln of sine of x to the power of x. Here we use another property of the ln function, and that's that ln of a to the power of p is equal to p times ln of n. So basically, this exponent can drop in front of the ln function. So that's going to be a limit of x, so the exponent goes in front of the logarithmic function, ln of sine of x. Now, just to make sure here, let's check what's happening. This factor goes to 0. As in the previous video, this is explained in more details. As x approaches to 0 from the right, the function sine of x approaches to 0 from the right, which means that this function makes sense, right? And when we're approaching to 0 from the right, the ln function drops to negative infinity. So this whole thing here goes to negative infinity, and what do we have? We have a 0 times infinity types of limit, right? That's indeterminate product. But we learned how to deal with that. So this is going to be ln of sine of x over 1 over x. Now any constant, any constant divided by something that approaches to 0 goes to infinity, and the numerator here goes to negative infinity, which allows us to use the L'Hopital's rule. And now this is just a standard procedure. Derivative of ln of sine of x is 1 over sine of x times cosine of x by the chain rule, divided by negative 1 over x squared. Now always remember, once you've applied the L'Hopital's rule, now you want to simplify this expression. So that's sine of x negative x squared times cosine of x. When x approaches to 0, the numerator goes to 0 and the denominator goes to 0. So here you can use the L'Hopital's rule again, but why using such a complicated method when we can rely to what we have learned in Cal 1, and that's the fact that x divided by sine of x, this ratio, when x goes to 0, this ratio approaches to 1. So we are left with the limit of negative x times cosine of x. As x goes to 0, that 0 times 1 is 0. Now here you just have to be careful not to make the following mistake. This is not the end of the problem, okay? what limit is 0? This limit right here. But that was not our question. The question was not what's the limit of ln of sine of x to the power x. The question was what was the limit of sine of x to the power of x. And where this limit appeared? This limit appeared right here. Okay, so this limit goes to 0. So now you have to come back here. This limit is approaching to 0, and now evaluate e to the power of 0 is equal to 1. So the final answer to our question is 1. Okay, the base was approaching to 0, the exponent was approaching to 0, and this limit converges to 1. Okay. Second example is limit of tangent of x to the power of 2x minus pi, and x goes to pi over 2 from the left. Okay, so as x goes to pi over 2 from the left, the new exponent here, 2 times pi over 2 is pi, pi minus pi is 0, and tangent of x, if you remember the graph of tangent of x, it's like this. So on and so on. So this is tangent of x is equal to y, and this value here is pi over 2. So obviously when x approaches to pi over 2 from the left, tangent of x goes to infinity. So the base goes to infinity. So this is a limit of indeterminate form infinity to the power of 0. Okay? The method how to solve this is the same as in the previous example. In order to drop this exponent, I have to rewrite this as e to the power of ln of the limit that we are looking for. And this is nothing else but e to the power of the limit of ln of tangent of x to the power of 2x minus pi. Here I didn't need this bracket. X approaches to pi over 2. So if I evaluate this limit, when this limit is going to converge to some number, I'm going to come back here and plug it in here and evaluate how much is that. So on the side, we are evaluating what is limit as x approaches to pi over 2 from the left of ln of tangent of x to power 2x minus pi. Okay. So we are taking ln here so that we will drop down the exponent, and here you should expect that you will get a limit of 0 times 0 times infinity, and that's indeed what's going to happen, because tangent of x as x goes to pi over 2, we said that that goes to infinity, and the logarithmic function is like this. So ln of x, when x goes to infinity, ln of x goes to infinity. So this one goes to infinity. Okay, so how do we solve this product? This is equal to the limit as x goes to pi over 2, ln of tangent of x over 1 over 2x minus pi. We already said that this goes to infinity. This denominator here goes to 0, so 1 divided by something that goes to 0 goes to infinity. And I have infinity over infinity, so we can apply the L'Hopital's rule. Here be careful, finding the derivative of the numerator. Don't forget the chain rule, so that's 1 over tangent of x times derivative of tangent of x, which is secant squared of x, over negative 2x minus pi squared times derivative of 2x minus pi, which is 2. Let's simplify this expression a little bit. This is limit as x approaches to pi over 2 from the left. We have negative 2x minus pi squared times secant squared of x over 2 times tangent of x. Okay, so what do we have? The numerator is approaching, so secant of pi over 2 is 1. This one goes to 1. This one here goes to 0. So the numerator goes to 0. So the numerator is getting smaller and smaller, and the denominator is getting bigger and bigger. So the ratio obviously is going to go to 0. Now once you have evaluated this limit, don't forget to plug it up here, because that's the limit that we were looking for. The limit was just the exponent of v, and now e to the power of 0, the final answer is 1. If you want, you can observe this, for example, from here. One over tangent is cotangent of x times secant squared of x over 2 times 2x minus pi squared, and cotangent of pi over 2, this one goes to 0, this one goes to 1, this one goes to 0, and of course you're going to get the same answer as here, right? Which means that the exponent, this exponent approaches to 0, e to power 0. The final answer of our question here at the very beginning is 1. And the final example is limit as x approaches to 0 from the right of secant x plus tangent of x raised to the power of 1 over x. Okay, so on the side here we can write that 1 over x goes to positive infinity as x goes to 0, right? That's obvious. Secant of 0 is 1, and tangent of 0 is 0, which means the base goes to 1 and the exponent goes to infinity. So this is an indeterminate form 1 to power infinity. Okay, so we don't know how much is this. And again, what are we going to do? We're going to rewrite this expression as e to the power of ln of secant x plus tangent of x to the power of 1 over x. And because the function in terms of x appears here, this is just going to be equal to e to the power of limit as x goes to 0 from the right of ln of secant x plus tangent x to the power of 1 over x. If this converges, if this limit converges, that means that the exponent is going to go to some constant, which we are going to plug it in here and finally evaluate how much this limit is. But in order to do that, on the side, we will evaluate what this limit converges to. Secant of x plus tangent of x to the power of 1 over x. And here I forgot ln, the most important part. From properties of exponents, this can be written as 1 over x, right? The exponent drops in front of the ln function times ln of secant of x plus tangent of x x goes to 0 from the right. But this is equal to the limit. It's already expressed as a function, as a fraction, sorry, ln of secant of x plus tangent of x over x as x goes to 0 from the right. So let's see what happens with this limit. Okay, obviously the denominator, we're just sending x to 0, so the denominator goes to 0. I already know what this sum approaches to right here. The sum approaches to 1, so ln of 1, the whole numerator approaches to 0. So right away I can apply the L'Hopital's rule, and this is equal to the limit as x approaches to 0 from the right. Find the derivatives in the numerator and in the denominator. Derivative of x is 1, so we're left with derivative of ln of u by the chain rule is 1 over u times u prime, so that's 1 over secant of x plus tangent of x times the derivative of secant of x, which is secant x, times tangent x plus derivative of tangent x, which is secant squared x. Now I'm reminding you for the last time, after you apply the L'Hopital's rule, check whether you can simplify the expression somehow. So what is obvious in the numerator is that I can factor out one factor of secant. So let's do that. And we're left with tangent of x plus secant of x over, I'm just going to change the order here just to be follow the same order as in the factor in the numerator, tangent of x plus secant of x. But now, having the same factor in the numerator and the denominator, I can cancel these two, send x to 0, secant of 0 is 1. So, come back here, the exponent approaches to 1, e to the power of 1 is equal to e. And that's the answer of this limit right here. You see the base goes to 1, the exponent approaches to infinity, and this limit converges to the number e.